Indexes are used to quickly locate data without having to search every row in a database table every time a database table is accessed. Consider the query select star from instructor where salary is greater than 40,000. How will you locate the relevant rows in the database if it is stored as a sequential file with records within blocks? Instead of going through every row, we prefer to use additional storage to save us some time while serving the queries. We say we create an index on salary column. The index can itself grow large, so we create multi-level indexes. There is a problem with multi-level index we saw in our previous lecture. The insertion and deletion overhead is too much. For every row that is inserted, we have to update the index so that the index stays current and successful. An alternative to indexed sequential files is B plus tree indexes. The name comes from the world of data structures. If you have already taken a course on data structures, you must have heard of binary trees, balanced binary trees, binary search trees, and so on. A specific data structure called B plus tree is found very useful and efficient in database indexing. So let's first see what a B tree is, and then we'll come to B plus trees. A B tree is a self-balancing tree data structure that maintains sorted data and allows searches, insertions, and deletions in logarithmic time. The picture that you see here is a B tree of order 5. Why order 5? You will see that there are 5 pointers that are possible to point to the child nodes. So basically a B tree is made up of several nodes. Each node contains some data items, and before and after the data item there is a pointer pointing to the location of another node. We'll look at this with an example in detail as we go from here. So a B plus tree is like a B tree but has few important differences. So in a B plus tree, leaves are connected. So there is a connection between the leaves to allow sequential access. So let us understand B plus trees. So here is an example of a B plus tree. So I have several nodes. All the nodes are of uh, the same shape where they carry some data item, and along with the data item there are pointers. So in this example, I have chosen a fan out of 4. So a fan out of 4 means that every node would have 4 pointers, or in other words 3 data items. These nodes need not be full. So as you see here, although I could put 3 data items, there's only one data item here, Mozart. And you see there are 2 data items here, whereas this node is full with 3 data items. The leaves are the most interesting part of a B plus tree, where the leaves have the index pointing to that particular row in our table. So here is the table that we want to access quickly, and let's say I want to access this table by name. However, this table is ordered based on keys. So how do I answer queries that are based on names very effectively? So for example, if a query comes as Mozart or let's say brand, then I know that the pointer just before brand would take me to the row directly where brand exists. But now to reach to brand, I start from the root node and take the first value, which is Mozart. And then I ask, is brand lesser than Mozart or greater than Mozart? If brand is lesser than Mozart, I would take the left path. If not, I'll take the right subtree of Mozart. So in this case, assuming an increasing alphabetical ordering, we have brand less than Mozart, so we go left. And again, we start from the beginning, which is Einstein, and then ask whether Brandt is less than Einstein. So Brandt is less than Einstein. So we come again to the left. Now we check Brandt and Brandt. They are the same. So we have got what we want. So we simply follow the leaf pointer and we should reach Brandt. So that's the whole idea. So if we were looking for Calipari, we would have still asked the same questions to reach to from Mozart to Einstein and from Einstein to Brandt, and then we would say that Calipari is bigger than Brandt. So we go to the right of Brandt and check the second item, which indeed is Calipari. Since it's Calipari, we'll take the pointer before Calipari and we would reach the record for Calipari. And we could, if we just wanted sequential access, we could directly jump to the leaf and go from left to right, and we have pointers at the end of each node pointing to the first data item of the next leaf node, and so on. So this way I could simply get ordered sequential access of all names if I want to. So that's another advantage of using B plus trees. So we call these nodes as internal nodes, this node as the root node, and this node as the leaf nodes. This is standard terminology from the world of trees. And this is how we create an index for a given table. Notice that there is a lot of overhead in terms of space, so we have to have so many extra nodes and so many extra pointers. So there is definitely overhead to store B plus tree indexes. But the beauty of B plus tree indexes is that one, it allows us sequential access to the column of interest, and also it allows us to navigate quickly to the node of interest. Another interesting fact about a B plus tree is it optimizes for inserts and deletes. So how would you, let's say tomorrow I get added into this list, let's say Venkatesh somewhere. So here, so if I get added, then where should my name get into this tree? So that's the next question. So we'll take a look at that with an example.